Tonight we're privileged to have Paul Messick present, and he's going to be talking on low noise amplifier design. Paul has spent more than 40 years designing all sorts of electronics, everything from scientific instrumentation, radar and RF receivers, audio measurement systems, MI and pro audio products, and a lot more he's long forgotten about by now. As a consultant or an employee, he has worked for a wide range of companies, including Dallas Semiconductor, the JPL Jet Propulsion Laboratory, M Audio, and Digi Design, and more. Paul was head of engineering at M Audio Digi Design and later founded Avometrics, which made production line and benchtop audio analyzers, and still do. Since moving to Australia, he has started Glassworks Audio, designing high-performance studio gear for his own brand and for other select clients. He's got quite a deal of experience and be a very worthwhile presenter for us tonight. So I'd like you all to unmute, if you can find your unmute button, which usually takes a bit of time. And then I'd like you all to welcome Paul along and thank him for taking the time tonight. Thank you, Paul.
Thank you, Paul. Thanks for having me. One thing I did want to say is I don't mind at all being interrupted if I go off in a tangent or I have not been very clear. If you have a question, probably someone else has a question, so it might help everyone if you hop in there and wave your arms and let's get any clarification there that we need. Let's see. How do I share my desktop? I have not done it in this system.
At the bottom of your screen, you've got share screen.
There we go. Sharing. There we go. Okay, here we go. So can you all see this?
Yes, we're now seeing your slide.
Okay, very good. So I was going to start with an apology, but maybe it's not in order here. I was going to say that I have been very bad. I've included a bit of mathematics in this presentation. I suspect that a lot of the people here will not have a problem with it, but please forgive me. And just note that the final exam is open book, so you should have no problem with that at the end of the presentation. So I wanted to start with a little bit of what we're going to talk about. We're going to talk about the types of noise that you might run into in electronics. Noisy resistors, which is all of them. Noisy op amps, which is all of them. How to calculate and minimize noise in design. And then I'm going to design a real mic preamp, build it. Actually, I've done it already. Make some measurements and see how we did relative to what the mathematics tells us. And at the end, an extra little topic, just a few minutes, during which I intend to trigger a singularity. The universe will cease to exist and will go out with a bang. So try and stay around for that if you can. So types of noise. There's one type, avoidable noise, which is all the sorts of things that you can, with careful design, good grounding, shielding, etc., can prevent. Ground loops, conducted noise, mains hum, etc. So we're not going to talk about that anymore. Then there's popcorn noise, which sounds exactly like its name, which is due to impurities in semiconductors, which have pretty much all been resolved over the decades. So you might run across a new old stock op amp from the 70s, which has some nasty popcorn noise, but anything modern isn't going to have that. So we're not going to talk about that anymore either. Then you have flicker noise, which is also known as 1/f noise, which is an issue in some kinds of designs. This is where the noise tends to rise as the frequency goes down. There's a frequency at which that noise rises above the noise floor, and that's called the corner frequency. It's less of an issue for audio because you have two main reasons. One is the ear is not terribly sensitive to very low frequencies, and the most modern op amps have a very low corner frequency. But you might run into some kinds of design where this is an issue, so it's good to be aware of it. But we're not going to talk about that anymore either. Uh-oh. Well, I'm going to have to wing it. Another kind of noise is shot noise, which is what's the typical sort of noise that you see with semiconductors. So op amps and transistors all have this kind of noise, which is due to the fact that electrons are not a fluid. They're little particles banging around in the semiconductors, and that banging around causes noise. And the last one is Johnson noise, also referred to often as thermal noise. This is a function that all resistors have, strictly based on the resistance and not at all on the construction or type of resistor. And that's one that we'll spend a bit of time on. Oh, well, there it is now. Okay. So Johnson noise. Again, this is what resistors all have. No matter how the resistor is made, they all have this much noise. They might have more, but they won't have less. And it's a fairly simple calculation. But what's interesting here, I don't know if you could see my mouse pointer or not.
No.
No? Okay. So you have K is this magic number. Some guys become very famous for having his name on it, which appears a lot in electronics. The temperature in Kelvin, so for nice round numbers, tend to use 300 degrees. That's basically room temperature. And the bandwidth of your system in hertz, so in this presentation, I'll typically use 20 kilohertz for that. You might have other bandwidths, but for most audio things, it's going to be 20 kilohertz. And then your resistance in ohms. So the noise goes up as the resistance goes up, because you can see that it's all multiplied by the square root of R. Few examples. So in a 20 kilohertz bandwidth, a 1K resistor just sitting there, nobody's doing anything with it. All by itself, it's putting out 0.29 microvolts RMS of noise, which is equivalent to, and we'll get into this a little bit more later, 4 nanovolts per root hertz. That's an interesting number to remember here, because we'll compare it to what some op amps are doing. Same resistor, but 10K, 0.9 microvolts, 100K, 2.9 microvolts, you're starting to get into some real voltage there. It is possible for that to get into the multiple volts range if you have a high enough resistance. What you won't do is get any power out of that. You're not going to be able to get your get anything powered with this, but there's a real voltage there, and it's noise, and it affects anything that's sensitive to noise. There's also a noise current. So if you were to take that same resistor and you put a short across it, you'll measure a current, which is this value. So the rule of thumb is the noise current will dominate when the resistance is high in a circuit, and the voltage noise will dominate for low resistances. And that will become interesting when we start to talk about a mic pre. There's another kind of noise that you get with resistors, which is excess noise. This is dependent on construction. So something like a carbon comp that we might have used in the 40s and 50s and 60s, that's literally where they've taken some carbon and pounded it into a cylinder and stuck some wires in the end of it. Those are pretty terrible for excess noise. Carbon film, much better, not perfect. Thick film, which is surface mount parts that you see very commonly, those are better, but still not ideal. Thin film resistors, which are constructed by sputtering basically metals onto a substrate, those start to be pretty good. And getting up to the gold standard of low noise for excess noise, metal film. The downside to metal film is they're very expensive and there aren't many values available. You can get a few standard ones, but they start to get quite difficult to actually buy. And then there's wire wound, which is just nitron wire, basically. You don't see that a lot in audio since they tend to also be great inductors. So thin film and metal film are where you tend to find the excess noise is not something that you worry about. There's also distortion that resistors will generate. This is a little bit of a nerdy, even more nerdy, tweaky kind of a thing, but it is real and I have seen it. And that is, hello? Are we? Oh, it decides I need to do something here. So resistors add distortion because there are little tiny microscopic cracks and gaps and things like that in the resistive material itself. If you think about them as being little areas that are in contact, there's a gap between them. And what happens is that voltage, as current passes through it, voltage will build up across those gaps, and they're very tiny. So they're small enough that you actually get arcing. And that's where you get distortion. So you get in terms of how much distortion you would get, you have basically the same ranking as you do for excess noise. Not going to spend any time with carbon comp. The carbon film, not too bad. Metal film, you're essentially not going to have any. Thin film, basically don't have any. Thin film, again, being kind of the sweet spot for this. One that is that if you're trying to do extremely low distortion that you try and avoid are the thick film resistors that are very, very common and very inexpensive because their very construction, they have these little gaps and they do add some distortion. This is only important when you've got distortion that's very, very low. I've run into it at distortion levels below about minus 110 dB. That's where this starts to make a difference, and it doesn't always, but it does sometimes. And the improvement that you might see is 1 or 2 dB. Really not a lot, but if you're trying to get the very lowest, best performance out of it, this can make a difference. So again, for very low distortion, avoid thick film, use thin or metal film. Bigger parts are better. I've seen some audio analyzers that will have parts that are nearly as big as your little finger to try and minimize any of this sort of distortion. You tend to want to avoid high precision. If a little is good, a lot is better. So if 0.5% tolerance is good, why not 0.1%? They're not that much more expensive. The problem is that those are actually trimmed 0.5% parts, and they trim them using lasers or they abrade the surface, which causes little cracks. And you're right back to the thick film problem. So what you'll see in pro audio for resistors tend to be thin film, 0.5%. I tend to use 0805. I don't see a lot of difference between that or a 1206 size. But if you're extra paranoid, you might use the bigger part. Any questions on this? Everybody's all right so far? Okay, good. Not asleep yet. So shot noise, which is what gives you noise in semiconductors, we don't really care too much about the maths here, but what is interesting is the noise goes up as the current through the transistor in this semiconductor, in this op amp or transistor, goes up. So the more current, the more noise. But on the other hand, there we go. For a transistor, so there's an inherent resistance that's in the emitter of a transistor. And that value is this formula here. And you can see that the current IC is the higher it goes, the lower the resistance goes. So more current means lower emitter resistance. And lower resistance means less noise. So more current meant more noise, but now more current means less noise. So therefore, everything is a trade-off. Everything you do in design is a trade-off, especially with things like low noise and low distortion. If you only have one noise source, it's easy. That formula before for KTBR, that's your number. But if you have multiple noise sources, which you do in literally any circuits you're going to actually make, they have to be added up, and they add up like RMS. They add up as the square of, hold on a minute. They add up as the square of each of the the voltages, assuming these are all independent. If they're different noise sources, then they're independent. If they have some characteristic where they're in some ways synchronous, then the math doesn't work out this way. It's slightly different. But for all the noises we're going to talk about, they're always independent. So you add them up, you take the square root, and there's your overall noise. For some reason, this thing keeps, there we go. So in an amplifier, you have this idea of the effective input noise. It's like you have a perfect amplifier and there's a noise source at the very input. So we refer to it as EIN. And when you're going to design an amplifier, you have a couple of choices. If you just wanted 20 dB of gain, then we wouldn't have this 10 dB pad there and everything would be fine. But you have a 20 dB amp in your hands and you have a 10 dB pad and you need 10 dB of gain. Do you put the amplifier first and the pad second, or do you put the pad first and the amplifier second? This is an important question because if you look at a mic preamp, for example, there's often a button on the front that says 20 dB pad. And that 20 dB pad is on the input of the mic pre. Just like, as I'll show you in a second, and where that's located will have an effect on the quality of that mic pre. So here's our fictional amplifier here. It has an EIN of 1 nanovolt per root hertz, so it's pretty darn good. 20 dB of gain is a gain of 10. So the noise out is 10 nanovolts per root hertz. And then we have this 10 dB pad. And in this example, I'm assuming that the pad is completely noiseless, just to make the math easy. So at the output of the pad, the noise is about 3 nanovolts per root hertz. So it's 3 times worse than the input is. But it's a third of what the noise is out of the amplifier itself. So that's probably a pretty good place to put it. To do the opposite, here's your 20 dB pad at the front of your mic pre. Again, it's noiseless, so I'm going to pretend it doesn't add any noise. So we've still got our amplifier here with the 1 nanovolt per root hertz EIN. So the noise out of it is 10 nanovolts per root hertz. That's a lot worse. That's 3 times worse than by only changing whether the pad is on the input or on the output. We've made the noise either better or worse for the same amount of gain. So when you see a pad on the input of a mic pre, I always cringe a little bit. It doesn't really matter because if you're going to switch that pad on, it's because you have a really loud signal. But it's not the ideal way to design a mic pre. In terms of minimizing noise, in terms of minimizing noise, these are the 7 steps to follow to get to low noise enlightenment. Keep the source impedance low if you can. So the thing that's driving your amplifier or your system. Keep the circuit resistances inside that amplifier as low as you can. Use thin film 0.5% resistors. If your source is a low impedance, and you're designing for that, more current in your amplifiers is better. And you want to choose op amps and transistors that have, you're choosing them for low voltage noise. If you're designing something for a high impedance source, like say the capsule of a microphone, then you need to choose op amps and transistors with low current noise. You're less concerned with the voltage noise. And again, gain first, attenuation later. So to get down to what's a practical circuit, op amps have come a long way from the days of the 5532. So there's one now, there's a whole series of them, but I'm going to pick one of these, the OPA 1612. They're not cheap, $5 USD each in low quantities. If you're buying them by the reel, they're about $3.50 for 5,000 on a reel. So be sure to bring your American Express card. This is a dual op amp. The OPA 1611, which is slightly cheaper, of course, is a single op amp. Interestingly, the quick side, part of why these are so expensive is to get the noise this low and the other specs this good. The transistors in the op amp are really huge. They're physically large, which means the die is very large, which means the number of them they can get on a wafer is small and the price goes up. And that's, I think, the biggest driver here for this. They're pin compatible with most of the other 8-pin surface mount kinds of op amps. There's a lot you could choose from. In a lot of cases, you could just do a swap with these and get better performance, but not always, because again, if it's a low impedance source impedance, this is an excellent op amp. But if it's a high impedance source that you're amplifying, this is probably not a very good one for that. So if we look at the specs, the voltage noise 1.1 nanovolt per root hertz, that's pretty much at the best you can buy in an op amp. There are a few really exotic ones that get down to about 0.9, but they're not very good for audio. So for audio, this is pretty much the gold standard. To compare it with a 5532, which literally costs 25 cents in low quantities, 5 nanovolts per root hertz, so much noisier. But the current noise of a 1612 is not great, 1.7 picoamps per root hertz, which seems like a really low number, but you look at the 25-cent op amp and it's 0.7. So that can, I actually had a design that was the output of a current mode DAC, very nice Burr Brown DAC. It was the IV converter of that. And the 1612 was lousy, and we couldn't figure it out until I realized that the current mode DAC was a very high impedance source, and this current noise was the thing that was the issue. We ended up replacing the $5 op amp with the 25-cent one and got performance that we needed out of it. So another interesting spec, gain bandwidth, which is the gain of the op amp multiplied by how wide a bandwidth it can amplify. So with a gain of 1, 1612 is 40 megahertz, and the 5532 is 10, which is not bad. When you turn the gain up to 100, though, the 1612 actually gets better. I don't know what a 32 does, but you start to run out of steam as the gain goes up. The bandwidth actually starts to come down. Slew rate, very good on a 1612, not bad on a 5532. Distortion is insanely low, 136 dB down. It's actually quite hard to measure this level of distortion. For most purposes, you can just say there's no distortion. So if we're going to make a mic pre, there are a few specs that are important. So for a microphone, those specs are sensitivity. So the output voltage versus the SPL that the field that mic is in. So that's normally specified as 1 Pascal
Excuse
pressure.
me, Paul. Excuse me.
Yes.
There are a couple of questions in the chat that
okay.
you might want
Thank
to
you.
respond to before you get into this.
Yeah, I don't see it because it doesn't. This screen. Let's see if I can. Yeah, this thing is in full screen mode.
Okay. Okay. I'll read them out for
Can you?
you. Yep.
Oh, here we go.
You found it?
Yeah, there's something. Let's see. Any questions about the OPA 2X series? Can you give me an example? You mean like a 20? I forget which ones those are. This was Paul Coven. Is he there?
I'm here.
There you go. So which ones are you referring to?
Like a 2134.
Oh, okay. So that's an older kind of a part. I mean, the 134 series is a fairly old design. I'd have to compare the specs, but they used to be pretty popular for this sort of thing 15 years ago. But I think the 1612s and the like have pretty much for this level pretty much done away with them. Now I think they're lower cost, if I remember, because they're, as I say, it's an older design. But they're probably not quite as good. I'd have to compare the data sheets, Paul, to really say. Sorry if
Okay.
that's sort of a non-answer.
No, it's okay. Thank you.
No worries. You say the 1612 is not as good as the cheaper op amps. Yes, I did. Luke, you caught that. Good.
I did, but I
It's-
was half not paying attention. But thank you for saying that, because we actually
I love the honesty. Thank you for that.
I mean, I'm not an electronics engineer, but I pretend to be one. And a board I'm working on the firmware for it has 1612s as current to voltage thing after DAC. So that might be worth a bit of research on our part to see if there's something cheaper and better.
Well, I don't know about cheaper, but the 1612 may not be the right part for that because it's not terribly well optimized for current noise.
Right.
They run huge amounts of current through the input transistors, which gives you nice low voltage noise. But the side effect of that is they're pretty lousy for current noise. There's actually a fair amount of current coming out of the part, basically.
I might get in touch with you offline to maybe seek some advice / consulting.
Absolutely.
Got the time.
Absolutely. Yeah.
Awesome.
No worries. Okay. Any other questions? Anyone that hasn't typed one in but has a burning question they want to ask? Okay, so I'll move on a little bit. So back to microphones, output voltage. they're surprisingly low. So 94 dB SPLs, they're not whispering. Right? That's a pretty loud signal source. And you're getting a typical output 1 to 10 millivolts. So it's not huge. So you need a lot of gain. I'm going to get this thing to cooperate. Okay. The other spec for microphones that's important here is self noise. So that's the noise that you get out of the microphone with no sound into it. And you'll find that mic manufacturers either measure this by disconnecting the capsule, which some people think is a sacrilege, or by putting it in a chamber where you don't get any sound in it. I suspect that it doesn't matter that the capsule's been unplugged because the capsule itself is just a capacitor. And so it by itself doesn't really do very much, but maybe some mic manufacturers would disagree, and I would defer to them on that. So sort of typical values for self noise, 4 dB to say 20 dB, 20 dB not being not a great microphone, but 4 is pretty good. That's what that means is that from a microphone that would be perfect and generate no noise of its own, that sample of a microphone would generate, say, 4 dB more noise than the perfect one. So that's pretty good. And these are typically measured A-weighted because that gives you nicer numbers, but it also matches what the ear does a little bit better. Nice numbers are good though. And an output impedance, which is typically around 150 ohms. I've seen some that were 200, 250 ohms. Don't typically see them a lot less, but they're in that range. So I'm going to use 150 in the calculations that I'm doing. So for a good mic preamp, we're going to need lots of gain, low noise. We're going to try and get the target EIN to be as close to, or if, stop that, or if possible, even less than the noise that you would just get out of a 150 ohm resistor, since that's what the microphone has. The idea being that if you can get well below that number, your mic preamp will add no noise effectively to your microphone. That's as good as it can possibly get. We'll see how we do, but that number ends up being minus 133 dBV and a 20 kilohertz bandwidth. That's a good number to remember because that's kind of your gold standard. Need a gain. I'm going to design one here that goes from 0 dB to 60 dB. 60 dB is a pretty reasonable amount. That's a gain of 1,000. Most mic pre's that you find that have a knob on the front will not go down to 0 dB, which is why they have that pad on the front. They will go down to say 9 or 10 dB. And this is because the pot can't go, as you'll see, to infinity. It has some resistance that it's maximum, and that sets what your minimum gain is. If you can go down to 0 dB, it's basically a line input at that point. So you can go from line input to 60 dB of gain, which is pretty useful. We need some bandwidth. I'm shooting for at least 50 kilohertz here at a gain of 60 dB. You might say, well, why go more than 20 kilohertz? Because most of us can't hear much above 8 kilohertz anymore. What do you need 50 kilohertz for? The reality is that even though our ears may be rolling off, we can still sense some things. And what we can sense is the problems with any weirdness in phase. So if you, I'm not going to refer to phase here so much as what's known as group delay, which is how much the phase is changing. So group delay is flat, the phase doesn't change. What that does for you is your ear is very sensitive to when things arrive. And if some frequencies, the sound arrives at one time and other frequencies it arrives at a different time, your ear picks that up. It doesn't know why, but it says something is wrong. So for the best imaging, you want the phase to be as flat as possible. So I'm going to push the bandwidth out so that at 20 kilohertz, the phase is extremely flat. And that's why I have that spec. Output level, maximum, the normal sort of a plus 22 that you can do with 15 volt rails, basically. And at 0 dB gain, line input plus 22 dBu. So here's our little mic preamp. This is based on the classic instrumentation amp. So you can see there, it takes three op amps to do this. One for each leg of the balanced input and then a summing stage. A few interesting things to note. The inputs are to the positive terminals of the op amp, which means the impedance looking into the op amps is as high as the op amp can do, which is a good thing. You're not going to load the microphone down. The gain is set by a single resistor here, RG. And I'll show you in a second how we choose what the value of RG. And otherwise, they're all the same value resistance, all 1Ks. Let's see, and the purpose of summing it down to a single-ended output out of U2A is that's how we'll get the common mode rejection that you want from a mic pre, which is any noise that's coupled on to the input that's on both leads of the balanced circuit coming out of the microphone. Those go up and down together, they get nulled out. So they don't end up in your output. So I've omitted all the usual things that you would have, like input protection. I did in experimenting with this, I did blow up a couple of op amps because I didn't have it in there. So it's important in a real one, but not in this. No filtering, no phantom power, none of those things. This is just the amplifier part of the mic pre. So you set the gain of this with RG. So if RG is infinite, you pull it out of there, then you get a gain of 1, which is our 0 dB gain. So we want 60 dB, then we're going to set RG to 2 ohms. I'm slightly wrong because I've now got a gain of 1001, but I don't mind. We'll see in a second that 2 ohm resistor is actually quite hard to get to 2 ohms. It's a source of difficulty. So, and then in most mic pre's that have a knob, well, all of them with a knob, there'll be a large cap that's in series with that resistor, that pot. because otherwise you get some voltage across the pod and you get scraping noises. They're very noisy with any DC on them. But as you can see, we've omitted that here because we're just going to plug a resistor directly into it. So there's our, just for reference, there's our little mic pre up in the corner there. We're going to talk about the effective input noise again. As a reminder, it's a noiseless amplifier with a noise source at the input. So that's how we model it. And so the total noise in the circuit is the op amp noise plus the resistor noises plus the input current noise times the source resistance. Because that microphone that's plugged into Paolo's XLR there is 150 ohms. So if there's any current coming out of those op amps, you're going to get some voltage in that 150 ohms. So when you set the gain up to 60 dB, what you realize here is that the noise from U2, the summing amp, and all those resistors just gets completely swamped by whatever noise you've got from the input op amps, U1, A, and B. So we can effectively just ignore all that other stuff for the 60 dB gain case. And we're going to pretend that they're all perfect because it's close enough. Since the noise from U1, A, and B are the same, we can add them like we talked about earlier as the sum of the two squares of the voltages. So that looks like this, very fancy. You end up with a noise of 1.56 nanovolts per root hertz. So the op amps, remember, were 1.1 nanovolts per root hertz, just the op amp. So the mic pre with two stages there and all that stuff ends up being only slightly worse. One of the cool things about these sort of amplifiers, by the way, a quick aside, is the noise of the amplifier itself goes down as the gain goes up, which is very cool for making things with a lot of gain. If you think about it, if we set RG to, and it shouldn't say 1R there, that's a mistake, but if RG is open, then the resistors all add up something and there's a bit of noise there. But as RG goes to 0, these are just shorted out. And so they effectively don't add any noise. And so you actually can see the noise floor of the amplifier at 0 dB gain, it's up here. And as the gain goes up, the noise floor goes down. Very beneficial. So 1.56 nanovolts per root hertz in a 20 kilohertz bandwidth is minus 133 dBV, which is a suspiciously interesting number we've seen somewhere before. It's familiar. So let's compare it to the 150 ohm resistor. It actually is the resistor itself is slightly more. So in theory, this mic pre might have a little bit less noise than the resistor that's inherent in the microphone that you're going to plug into it. No matter how good or bad that microphone is, this mic pre will be a little bit better. So here it is in all its glory. take that in. Believe it or not, this little mess works pretty well. I had no expectations when I assembled this. I thought this thing is going to be just lousy, and I'm not going to have a presentation here at all. I'm going to go down in flames. But you look at some of the measurements I took. Gain 59.7. That's because 2 ohms is pretty hard to get in a breadboard like this. You can imagine plugging, you can see the 2 ohm one on the far left there. He's just kind of hanging out in air, plugged into this. It's not really 2 ohms, it's something else. So 59.7. Frequency response is 3 dB down at 80 kilohertz. That should, for some of you might ring a bell, because at gains of 100 or more, that op amp has a gain bandwidth product of 80 megahertz. So with a gain of 1,000, 80 million divided by 1,000 is 80,000 or 80 kilohertz. And sure enough, that's the bandwidth of this op amp, of this amplifier at full gain. Input level at full gain, minus 40 dBV. That's about just below clipping. So the output level, 21.9. Our target was 22, pretty close.
Paul,
Yes,
it's Rodney.
yes.
You mentioned dBV, which is a reference voltage of 1 volt, as I understand it, but DVU,
Yep.
that's 0.77 volt or 1 milliwatt in a 600 ohm
So
circuit.
I thank you for asking this. I was hoping someone would ask. Back up here. So you'll see me switching between dBV and dBu quite a bit. I use dBV because it's more intuitive, because most of these are voltages, and dBV is indeed, as Rod says, dB relative to 1 volt. So 0 dBV is 1 volt, plus 6 dBV would be 2 volts. Minus 40 dBV is a millivolt, right? Did I do that right in my head? So that's convenient when you're dealing with voltages. Back in the day, everything used 600 ohms, and we had transformers everywhere, and we were actually driving power. And so the spec for audio was 1 milliwatt into 600 ohms, and that was 0 dBm, right? dB milliwatt. And when transformers went away and 600 ohms went away, we still wanted something that was a similar number, because there's a lot of gear out there. We're used to a lot of gear, and it has certain specs, and we'd like those numbers to all kind of be the same, because the marketing department gets involved. And so some bright spark came up with the idea of dBu, and the U means it's unterminated, I think is what it means. It sort of means unknown. It's the same number as you would get if you were measuring in dBm. And so the conversion between dBV and dBu is the 0.775 that Rodney refers to, which is about slightly over 2 dB, 2.2 dB. So you can take a value that's in dBV, and you can convert it to dBu by adding that magic number. And so you see plus 22 dBu is about plus 20 dBV. So I'm sorry if that's confusing it's confusing to me. It might be an interesting topic sometime to do the here's what dB is, because dB is a very confusing thing. Talking about it in terms of volts when it only means power anyway is a little bit
Uh,
of a problem.
DBV, I think, is part of the IEC standard and the Australian standard. DBU came out with, I think, Tascam and the Japanese manufacturers. A lot of broadcast equipment about that time, the Neves and those sorts of consoles that were still transformer led, operated at +4 dBm. And that
Right.
sort of doesn't get translated into the more modern equipment. So it's basically the Japanese manufacturers who came out with
Okay.
the DBU.
Okay. Yeah. Well, the main driver there is with the older gear, you were driving power into to a known impedance. It's 600 ohms here. But with newer gear, what you have is a low drive impedance and a high load impedance. So if the output of your device is a impedance of, say, less than 100 ohms, and your input impedance is 22K or something like that, power is not an issue here. But you like those numbers to work out the same so that you can interoperate with older gear and newer gear. And so that's where the idea of DBU came from. And it's pretty much become the standard certainly in pro audio. Everything is in DBU. But for the mass here in design, you often use DBV just because you don't need to convert back and forth between DBU and DBV when you're dealing with volts.
Can I offer a slightly cynical view?
Yes.
That in noise specifications, if you use DBV, you get a 2.2 dB higher figure.
Marketing got involved.
DBU. We're very good for the consumers.
Yep,
deceiving them.
Well, you're absolutely correct, and I am slightly cynical in this way as well, because I have it is something that when the marketing material gets written, choices need to be made, and it's quite common to make the choice that gives you the better looking number. That's why you see a lot of things that are specified in with A-weighting filters. A-weighting, we're sort of addicted to it because we get better numbers that way, but it isn't always particularly a good representation. In fact, sometimes you see adding an A-weighting filter and your noise goes up as you measure it. You see that quite often when you're dealing with extremely low noise, because there's actually a 1 dB gain at a kilohertz in the A-weighting filter. So that can actually make your noise look worse. But it's the same sort of idea.
It also doesn't work so well because that A weighting is based on the threshold of hearing. And as your level goes up, your hearing tends to flatten out. So
it's true. That's certainly true. And so as I say, we're sort of addicted to A weighting because when you're going to measure something and put the specs on a data sheet, or you're going to put it on the website for here's how great our product is, everyone else has been doing A weighting, and so you're sort of forced to do A weighting too. And the chips you're buying are spec'd in with the filters built into that, and so on. But it's good to be aware that yes, there is a certain market aspect to this. And as engineers, you kind of know, I turn the filter on and off. Check it with it, check it without it. I have a nice Apogee 20 kilohertz filter that's extremely flat, and that's a pretty good standard for measuring this sort of noise. So yeah, you're absolutely right. Any other questions? Okay. Oh, there's one. It's this. See, the feedback resistors are 1K, assume for low voltage noise. Is that a trade-off with the headroom? OPA specs show minimal headroom with 2K load, but I suppose that's noisy. Well, so good question. The OPA 1612 can actually drive at its distortion spec, minus 136, rail to rail into 1K. I think it actually will go down to 600 ohms, but it might not quite get rail to rail. But I know that it does rail to rail into 1K. And so you see that is a pretty typical number for things like feedback and load resistances. In the case of this design, I use 1K because in just the next slide, we're going to do the 0 dB gain version. We're going to take RG out and we're going to have a 0 dB gain. So it's a line input. And that's when that 1K starts to kick in. And I actually did breadboard this with 2K just to, sort of double check my sanity. And it doesn't make any difference with high gain, of course, and did make a difference. It's 6 dB worse. So, sorry, 3 dB worse because it's a summed as a square. So the noise got 3 dB worse at 0 dB gain. So since the OPA 1612 has no problem driving 1K, I've left it at that. Does that make sense? I think it was Greg that asked that. Good catch. Where are we? I'm lost. Help. Here we go. So we're gonna yank the RG out of there completely. So it's infinite. Gain is 1, so 0 dB. Measuring it with a 22 dBu input, just for fun, because that's the industry standard for level. THDN 120 dB, which is as low as my analyzer will go. So it's probably lower than that, given that those op amps are spec'd at 136. But you've got 3 zeros, so that's pretty darn good. Of course, A weighted, it's slightly worse with the Apogee filter. Not a lot. I think it was like 117 completely flat. SNR 136 dB, A weighted, again slightly worse without the A weighting, but not by much because it's just white noise. 136 dB SNR is pretty darn good for a line input. So how'd we do? When pretty close on gain, that we're off by a little bit because that resistor at 2 ohms is not 2 ohms. Pretty close on EIN. Now, here's an admission of error on my part, one of many. So I calculated it was going to be 133 dBV. So we're 1.3 dB off. what I realized later was I'd had the analyzer set to a 150 ohm source impedance because, hey, it's a mic pre. But that means that I built into the measurement the noise of the 150 ohms. If you were to measure it with a lower impedance source, it would be better. And in fact, going from just calculating it, if you went from the 150 to the lowest that the AP will do is 40 ohms, that's about 2 dB. And sure enough, if I measured this, unfortunately, that circuit's long gone. But I've been working on something related, and it did indeed drop by about not quite 2 dB. So we're probably right on the money with what the calculation said. It's just my poor job of making the measurements that's an issue here. Pretty close on all the other specs. I give myself a thumbs up. And there's a very high performance mic pre built on a breadboard with the wires hanging out in the air. It's pretty much on par with the best of what you can buy. In fact, there isn't anything close to this. This is a side effect of this whole conversation is a side effect of I've been working on a mic pre that's like this for some time. And in this presentation, building this cheesy circuit, finding that it worked so well kind of unlocked a lot of the things that had been blocking me, and that mic pre is underway at this point. And the intention there is that it be a product that is better performance in every respect than anything you can currently buy. And this little circuit with 3 op amps is pretty close to that, I have to say. Question here. Iorin and Paul, it's Paul Coven again. What's your impression of using 8620 instead of I don't have one because I haven't used that part. These are interesting parts that you're finding. I will say that I had done a canvas of basically everything that was available about 10 or 12 years ago. And this was about the time that the 1612 came out. And for the sort of designs that I've been doing, it's pretty much the perfect op amp. But you may find other op amps that are better for a given kind of circuit. So I don't know that particular ADI part, but you'd have to look at, based on what you're trying to design and what your goals are. So sorry, again, not a very good answer, but best I can do.
It's a stereo pre, Paul. It's not a mic pre.
So that's the stereo pre. You mean it's like one of those parts that is missing some of the other bits and you have to build it out from on the outside?
Well, stereo, a preamp system for your home stereo situation. A lot of line-ins.
Yeah. So it's like a moving coil cartridge sort of preamp, that kind of thing.
Right, or tuners or CD players.
Yeah. I mean, you'd have to look at what the specs were. There have been a lot of those around. The ones that aren't complete instrumentation amps or at least complete op amps can have better specs in some areas and worse specs in others. So those were designed for a particular thing, usually for stuff like a moving coil preamp, where they're looking for a specific performance specs and they're trying to make a filter around it and of a certain shape and so on, which is why they tend to not have all of the op amp innards in them. So you're asking about PSR. So they're all going to be pretty similar. Most of these kind of parts are going to be, he's asking power supply rejection ratio. And that one is I'm going to call that one as being in the avoidable noise area. But I'll say that the op amps that you typically find are going to have a PSRR in the say 80 dB kind of range. So depending on your rails, like sometimes I use if things are extremely sensitive, I'll use an extra linear regulator after whatever is coming in, like a switcher. I find more recently that's been less important to do, but it matters more for things like the voltages that drive the analog part of ADCs and DACs and things like that, because they actually tend to not have very good PSR there. Does that answer that question? I guess. Okay, so a few things that we might think about doing to improve this or make changes. You could, the common mic pre has front end matching pair of transistors. You run a heap of current through them. You get a very low, what's known as base spreading resistance. And you can get EINs. If you recall, I was saying the EIN's about 1.56 on this mic pre. You could drive it below 1 fairly easily that way. I say fairly easily, having run into all kinds of problems with that, because these sort of op amps also have an enormous amount of gain, and you add some more gain in front of that, and what you tend to make is a nice oscillator. And so I have a design that is, as I'm talking about here, with the transistors in front of them with a very low RBB and an op amp after them, and all the servo loops to set voltages, et cetera, et cetera. And I think that the op amp is oscillating actually inside. You can't see it on the pins, but the noise and distortion are not what they should be. So it's not a panacea. If cost is an issue, when this thing is not cheap, there are some other op amps you could use. You could use a 1656, which is about a quarter the cost of a 1612, or 5532. And there are lots of mic pre's that were made with those. It's not a great mic pre, but it's an inexpensive one. And you'll see that sort of thing at the input to a lot of prosumer sort of gear. You could build it on something a little bit better than, CZ breadboard. We'll see how that works. I have a PCB coming of something that's related to this design that should be here in a day or two. We'll see how that turns out. And if you're going to do the the typical variable gain pot, you need a big series cap with it, which will introduce all kinds of other problems. One of the problems is that gain pot is extremely nonlinear. You can't get a pot with enough of a log curve to it to actually compensate. So most of the gain chain is no gain change, no gain change, no gain, a little bit of gain change, a little bit, and you're at full gain. So that's because you're dividing by that resistance. So as that resistance goes down, the gain goes up rather rapidly. So there are issues with just sticking a nice pot in there. I think we have enough time. I'd like to do a quick extra 5 minutes. There's another view of noise versus my favorite, the audio marketing machine. This is 32-bit DACs and ADCs. So everybody's got a 32-bit DAC and a 32-bit ADC, and they think they can charge more because it's got 32-bit on it. And a lot of products now, you're forced to say, oh, they're 32-bit. And so let's see how the marketing hype stacks up against actual physics. So you think about the dynamic range for a pretty good DAC, 120 in 20 dB. A very good one, say 128. They could even be higher. How many bits are getting here? So there's the math. Effective number of bits. A bit of log for you. So for the 120 dB case, there are 1 million possible states. So 1 million is the highest value. So the number of bits being used is almost 20. So 128 dB case, it's a bit more than that. So the number of bits is 21.3. So if we're using 20 or 22 bits, what are all those other bits doing? A lot of nothing. That's what they're doing. But let's do some more math. Let's assume we have the marketing department turned out to be correct, and it really is 32 bits, and it uses all the bits. What sort of resistances would we have to use to match the performance of that ADC or DAC? So the signal to noise for 32 bits is 192 dB. So it's not bad. So if we assume output levels plus 20 dBV, then the noise, the input noise that corresponds to that is minus 172, which is 16 picovolts per root hertz. Now, remember the other stuff was in nanovolts per root hertz. So we're in a whole other class here. The resistance is just rearranging that formula from before. So for 16.4 picovolts, that requires 16 milliohm resistances. And probably you don't have an op amp that's going to drive that. You don't have a microphone with that sort of output impedance. This doesn't work. So what if we cool this thing? T is one of those values there. So let's dip this thing into liquid nitrogen. Now, this isn't that much of a joke. I worked on a radio telescope that the optical stage did exactly this. It sat in a bath of liquid nitrogen and then had a little tiny heat pump, like mouse-sized heat pump that would cool that optical stage down 0.25 degrees Kelvin. It was at the time considered to be the coldest point in the universe. So we do that to our codec and we get 0.12 ohms. We're still not doing it. Sorry. What about the heat death of the universe? Would that do it? If we get it down to 1 degree Kelvin, what sort of resistances is this going to take? Almost 5 ohms. So, yeah, well, we're getting to something. The only problem is at that point, the universe has ceased to exist, and all that's left is bang, we're done. So, that's my presentation. Any other questions? Did we get some? What about comparison single-ended, discrete, non-op-amp design? Well, those are good if how do I put this nicely? There's no advantage to having a bunch of resistors and transistors and whatnot out on in surface mount on a board versus something that's monolithic if the performance is the same. Except it might be cool to say I have a class A discrete mic pre, which some people want. But I don't think that there's an inherent advantage to doing something discrete in the modern day. That now I say that because once upon a time that was the only way to get this to go, and in some cases, like if you wanted to optimize this sort of a mic pre for cost, you want to drive the cost down but not lose a lot of performance, then you probably need to look at different op amps and transistors in front of them and do that more classic mic pre design, which is kind of a hybrid discrete op amp design. Are you thinking in terms of any particular mic pre that you?
Well, it goes back to the, dare I say it, the days of the dear old EF86 and the transformer.
Yep.
If you're having a balanced input using a pair of op amps, that means you've got 2 active components in the signal path instead of 1. The only mitigating factor is you're dividing the effective resistance of the source by 2.
Mm-hmm.
And then with the gain, the noise adding on power and gain adding voltage wise, you can end up back at the same point.
Yeah, but I would say that if you do a balanced design with a long tail pair, which is the typical way of doing it, you still have 2 devices there.
Yep.
So if it's balanced, you're not going to get away from that. And then you're going to get the noise added from both of those because those both have to be part of the signal paths.
Yeah, I'm very retro because I do remember Transformers.
Oh yes.
Yeah.
Well, there are serious advantages to Transformers. Yeah. I don't want to minimize that. Well, I'm sorry. Go ahead.
Well, Graham Cohen came up with his transformer-like configuration, which is very much the balanced instrumentation style that you have there, and the common mode stage, which in fact John Grau of Millennia actually adapted for his very successful line of mic preamps. He said he owed Graham Cohen a bottle of red, but I don't think he ever got it. But configuration is very much part of the success of the design, as well as the noise and its utility.
Well, yeah, I won't disagree with you.
Pity.
Yes, well, what I will say is there are different philosophies on what you might want for a mic pre. So if you're looking for kind of a vintage sound, what I'm doing might not be that interesting, because I'm basically pulling the distortion out, and the vintage mic pre is likely to have a fair amount of distortion. That's not undesirable in some cases. What I notice in the market, though, I'll say, and what sort of pushed me in this direction, is that people don't necessarily want something with its own sound, because they're going to drive this thing into Pro Tools or whatever their DAW is, and they're going to have a million plugins that let them emulate anything that any piece of gear that you could ever have lusted for. They have a plugin for it that does a very good emulation. So the drive to have a piece of outboard gear that is has its own sound seems to not have as much of a market as for to be able to just play it into your DAW with a plug-in and you're at Abbey Road.
Yeah.
John, you'll be right, because you can still buy EF86s, and they've started making 12AU7s and all of those valves. So you'll be right. You'll have the choice.
Too late. As an octogenarian, I'm not going to be sitting down at the soldering iron.
We probably need to take these questions offline. What I want to do is I want to really thank Paul for most interesting stuff, and I love your sense of humour. I like the Big Bang. You could talk about the R2R networks inside the ADCs and DACs too, but anyway, it was very, very interesting stuff. And I'd like everybody, can we unmute? I don't know whether Peter can do that, but I'd like you all to thank Paul for taking the time and giving us a very informative and entertaining session tonight. So thank you very much, Paul.
Thank you, Paul.
Thank you.
Now, probably at this stage, I'll close the meeting, but if you want to continue on, it's probably okay. Was there anything else to cover, Peter?
No, I think that's it. I'll hold the I'll hold the meeting up because I can hang around for another half an hour or more if a select few want to chat with Paul and give his pearls of wisdom.
We should ask Paul whether he can stay up.
Well, absolutely, and feel free to grill me as much as you want.
Oh, good. Okay. Well, thanks very much. The meeting is now officially closed and unofficially open. And I see you there, David. So David Hudson. So
hey, David. There you are.
Hello.
My apologies for late joining.
No
Still
problem.
not quite well, but I'm getting there. Forgot all about it. Sorry.
No, you're fine.
Big day. I saw Anne today. First time in 10 days or more. 2 weeks.
Welcome.
All good. Yeah. Getting better. Yep.
All right.
That's good. We got a question there from 36995. Who's that? Who's 369,895? Can we unmute?
He's muted.
I'm unmuted now, am I?
There you go.
Now, yep.
Do you hear me?
Yeah.
Yep.
You haven't. I'm not seeing myself, right? There I am now. Yes. Okay. Now, look. First of all, thank you very much for the talk. It's lovely to see someone that actually puts some reliance on maths and calculations of things.
Yes,
the ability to calculate things is terribly important. Now, there are a couple of things, really. First, I have to say I've been out of audio for 20, 25 years. so I'm completely out of touch with the numbers and things that people are talking about these days. Really, I've got 2 or 3 questions. First of all, the preamplifier, you said it was a 150 ohm output, and somewhere you said it was a capacitor. Now, I'd like to know, I assume it was a capacitor microphone. What was between the capacitor microphone and that 150 ohms? Was it, for example, a source follower buried inside the microphone?
Well, it depends on the microphone. Obviously, most microphones have some sort of an amplifier if they're a condenser type, that sort of capsule. So they'll have some kind of an amplifier. Often it's a FET amplifier. Some of them are tube, believe it or not. Some of the most coveted ones. But there'll be some sort of amplifier. So its output impedance of the microphone is typically around 150 ohms. But the capsule itself will be, it's a capacitor. It's an open circuit.
It's typically a few picofarads, which then really says what we should be looking at is the noise of what goes between that capacitor and the external amplifier. So that the things that you've been talking about are, we'd like to learn more about those. A second thing, one of your calculations, I think, was a slip. I used to know about resistors and capacitors and could do calculations in my head. You said a 4,700 microfarad capacitor for that 2 ohms. I think you've dropped a factor of 10. I think it's about 50,000 microfarads that you need for that, to get the hertz response down to something like 20 hertz. Check it out, but I think it's much bigger than you actually said there.
Well, what I'll say is there are a lot of mic pre's that are out in the free world that are the actual way that you do that is you take 2 91,000s or 2 10,000 microfarads and put them in series with the positive terminal in the middle, and you bias the center so that you're not crossing 0 with a electrolytic, which is nasty for distortion. So you end up with something around 5,000 microfarads. This is an issue, though, that you run into mic pre's that are a little light on the low end because they have this cap in there. The designs that I'm working on omit that completely, but I don't use a pot. I use relays and resistors, and I don't have any of that. So it's DC. It has gain down to DC.
Would it be okay for me to introduce you, Ed?
If you wish to, yes.
Yes. I don't know whether everybody realizes that this is Professor Ed Cherry.
Hi. Very good.
You look wonderful, Ed. You look wonderful.
Graham, you saved me the embarrassment because I was going to point out that 60 years ago in Alekhine 3, I proofread the early draft of electronic engineering by one Darryl Hooper and Ed Cherry.
Yeah. We all thank you very much, Ed.
Well, it's good to be with you again. I think my opening comments are perhaps the things that I would like to emphasize. And thank you for the talk that you've given us because you emphasized calculation. And that to me is the important thing. If you can, I believe calculations all time over suggestions, or and I come back to say if you measure something and it doesn't agree with your calculations, then something's got to be wrong. And usually that's right, the measurements rather than the calculation, assuming they were done decently. Thank you.
Well, exactly. I'm an electrical engineer. I'm not a hobbyist, and it's so I come at it from you design something and then you build it. Although I did build this I think I actually assembled something first just to see if I could even get it to work, and then it was like, okay, that's working, and then you go do the design. and you don't have anything until you've actually done a design. So yeah, I would agree with you with that. Absolutely. So,
so one other practical thing, when we were measuring low noise amplifiers, this is going back 25, 30 years ago, having them sitting on the bench on those plug-in boards, the noise that we measured was completely overwhelmed by what we picked up from around the room. It wasn't electrical engineering. Now, your thing sat on the bench. What did you have in the way of shielding around it when you got to those measurements that you took?
None at all, but I have my little lab here, which is about the size of a closet, stuffed to the gills with gear and me. I've learned what things I need to turn off to get rid of what noises, and so even though I show you that picture with the lights on, that was actually most of the measurements were done with certain lights turned off because of that exact problem. But this is basically what I do all the time. So I've kind of gotten, although I don't use that kind of breadboard typically, but I certainly have over time figured out where the noise sources are. And there's certain pieces that I know if, I see that noise and I know I need to go unplug that thing. So it's a constant battle. Absolutely. Normally I would have a PCB layout and I have a jig that I can put these on that has a good ground plane and so on to actually get that noise down. But I do look at the FFTs of this to see if there's anything that shouldn't be there. And for example, mains will always show up, and then you have to go through a process to figure out what was wrong with the grounding and correct that grounding, because none of those measurements will be right until you've gotten rid of that. Those are all the avoidable noises.
Come on.
Hmm? Who was that?
I know.
Okay. Yeah. Let's see. There were array transistor with a low RBB, NPN, PNP part numbers. Yes. You can ask me this from memory. If the part number's it's a ZL something. Let's see if I can think of where if I have it near the surface. Actually, I might. I can tell you because it took me a while to find it. I will say one great source that I found for information is a book called The Art of Electronics, which has lots of interesting things in it, including some charts about noise in transistors and base spreading resistances. So let's see, what is this? ZTX 951. It's a PNP. To answer that question, you'll typically find PNPs to have a little bit better noise in that respect because their base spreading resistance tends to be a little lower, but there is an NPN variant of that. It's literally a power transistor. It's not made for low noise. It doesn't even have noise specs. It's basically just a very large base, very, kind of transistor. It's a power transistor. And so you find a lot of low noise transistors like that end up being power transistors because the dies are just so large and you can run a lot of current through them. Let's see what other question do we have. Makers of ribbon mics have some degree of amplification built in where they tend to use. Do you have preferences? So I don't really do the mic design myself, but Wes Dooley, somebody I used to know. I think he's retired now. I know he's sold the company. But all those sort of, I'm sorry?
Company's still active. Wes is still up.
Is he?
Yeah.
But he sold his business, didn't he?
That I don't know, but I do know the company is still growing, still doing very well. He just did a local presentation for AES recently.
Wes did?
Mm-hmm.
Awesome. With in his suit with the
no,
the top hat. Not with the top
no, not
hat.
in the suit.
Oh well.
No, he and his wife are still running the AEA. Still running the
yeah.
Still running
Oh,
AEA.
okay. I thought he sold it, or
Yeah,
he might have, and then he's been pulled back.
Yeah, I've known Wes on and off for 40 years.
Okay.
So,
yeah.
No, but I know he's still up and active, and AEA is still very active.
Yeah. Okay. Good. Well, so the what you tend to find for mics that have a high impedance capsule like that, or element, is that they will use a FET at the front end. That's usually whether there's any gain beyond the FET depends on the particular mic, I think, but the typical input is a FET to get that. Obviously, with an FET, you've got such a high impedance, you're not going to really see any current noise, which would be the issue with, and certainly not loading, which is also an issue with a microphone like that.
I'm going to take it back to my dear old theory time, and there was noise matching in terms of matching the noise performance to the impedance of the device you're amplifying.
Right.
And you have the falling curve of the voltage noise and the rising curve of the current noise, and in the middle there's a eutectic point, which E over R gives you an optimum R for that particular device.
Right, it's absolutely true, but it depends on the impedance, right? So if you're in a kind of mid-range, that works extremely well. You can find a minimum there.
Yeah.
What you'll find is if you're at one end or the other, you can't find a minimum, because the minimum for the device will tend to be in the middle, and you're actually over on one end.
Well, that's why the ribbon microphone is so challenging and so interesting, because it's such a low impedance device, but at the same time, all its impedance is reactive. So the resistance component of the noise can be very low, but you've then got to match your amplifying device to that situation.
Yeah. Well, as I say, that's not an area where I've done any work. The microphone side of this, there are lots of people doing it. We did some of that at M Audio, but we had somebody from outside actually doing that design. It's a bit of a thankless task.
Oh, yes.
It's a difficult market, especially if you're trying to compete with long-standing brands that are already there.
Particularly if you're hit by the audio marketing mafia.
Yes, well, there's always that. But we had some trouble getting much traction, because you're trying to compete with these existing brands, and there's a fair amount of conservatism in the audio world, I'll say.
It's the point where science disappears and art takes over.
Oh yes, well, don't get me started there.
All right, Paul, thank you very much for a fascinating look. If Greg Siegel's around, he will remember me as being somewhat of a noise Hun, as you might say.
Yeah, well, noise is interesting to me. It's because it is a challenge.
Yeah,
and it's basically just fighting physics.
Yeah, my noise experience was partly audio and partly multi-channel telephony.
Yeah, yeah. Well,
that's more fun.
Audio.
That's audio. That's power.
Audio.
Power. That's where the power side comes from.
Yeah. Right.
Anyway, thank you very much for an interesting insight into electronic design.
Thank you. Okay. Well, I'm certainly glad that there were so many people that were interested, and interested at a high level. So this has been heartening for me. One reason I'm trying to pass on some of what I know is much of these topics are not how do I put it? They're not popular in school. The cool kids don't take these kind of classes. So as far as I know, there really aren't the people teaching this sort of stuff, at least in the undergrad world. And I think that we're at risk for losing the skills that you need to do this kind of work. But the desire for the products to make music, record sound, reproduce sound, all of those things is still there. But there are fewer people that are able to do it beyond just, I'll take some parts off of a data sheet, take their design, and I'll make some product. Yes, that's doable, but that's not engineering necessarily. So thank you for having me, and thank you for being interested.